Thanks all for coming, and especially thanks to Mark, our guest speaker, who managed to find the time to speak to us today. Mark is one of the world's foremost experts on programming languages and security. And he's also done groundbreaking work on programming languages and economics and finance. He's one of the leading lights on smart contracts, for example. He's the inventor of the concept of OCAP, of object capabilities, which is combining the classic notion of capabilities with objects in programming languages. He's done great work on distributed systems, on logic programming, and I probably am forgetting lots of other things, but it's a real pleasure to have him here. He'll be talking to us about some of his work that's really going to impact all of us in terms of securing JavaScript. So without further ado, I don't want to waste any more of Mark's time. Mark, take it away.
Over the course of my career, I've seen us figure out how to get software more and more right. And the more we figured out, the more value we contributed to the world. If we were getting computer security right, we would expect the security situation to be getting better over time. However, that's not what we're seeing. The red bar there is just the graph as of July 1st, 2021, and it's already worse than all of the other bars on the graph. Well, what about this magic world of crypto and blockchains we've been hearing so much about? Agoric is a blockchain company. Does blockchains give us the magic secret sauce we need to solve the security problem? Well, not quite. Blockchains do solve an important problem, and crypto, of course, solves many important problems, but it solves those problems at a low level of abstraction. Blockchains give us the equivalent of a credible computer built by massive multi-way agreement of many physical computers together with cross-checking consensus protocols. But even with a credible computer, if the programs you run on that computer are insecure, then you still have security problems. What blockchains do, what the modern world of permissionless crypto commerce does, is it raises the stakes. It means that if those programs that you're running, if, for example, DeFi, decentralized finance, if your decentralized finance smart contracts have an exploitable flaw, hundreds of millions of dollars can disappear overnight with no recourse. Agoric is a blockchain company in which we're building various DeFi products, so we really need to get this right. That number on the screen is not a typo. It really does say $2 billion lost through DeFi bugs just in 2021. Crypto commerce is not just about the blockchain. It's also about the software running elsewhere that talks to the blockchain. The event stream incident is a very nice example of some of the issues that arise. There was a crypto wallet called BitPay that was built on Node using the NPM Node package ecosystem. There was a malicious upgrade to one of the packages that was specifically targeted at stealing BitPay's cryptographic keys. This kind of software supply chain attack is quite a serious threat. This over here is the package dependency graph of another crypto wallet, MetaMask. And the purple dot there is the software that's specific to MetaMask. All of the other dots are third-party packages that are linked in. And this is typical. the normal JavaScript application, only about 3% of the code is specific to the application. 97% is linked in from third-party packages. And in normal JavaScript, in JavaScript as it's conventionally practiced, everything is vulnerable to everything. Any one of these packages that is malicious, or even that is buggy in such a way that an attacker can exploit it. Any of those endangers everything. Fortunately, MetaMask itself is using hardened JavaScript, which is the central topic of this talk and which we will come back to. Okay, so BitPay was running on Node on the JavaScript server. What about the browser? There's been all sorts of work on browser security. Well, this is a snapshot of the browser security problem as of 10 years ago, before another 10 years of accreting complexity. And even back then, it was so much never-ending complexity to practice security in the browser in the conventional way that it was really pretty hopeless. And the experience of security on the browser has confirmed the hopelessness of that. So, are we doomed to never-ending tinkering? Well, if you approach it with the wrong premises, we are. The Greeks approached astronomy with the premise that the circle was the most perfect shape, and therefore the orbits of the planets had to be built out of circles. But they didn't quite fit circles. So Ptolemy came up with this notion of epicycles, of circles on circles. And that seemed to work until people took more accurate measurements. And they couldn't fit that to circles on circles, so they had circles on circles on circles. And every time you had more accurate measurements, every time you delved deeper, you find that you had to keep fiddling in order to make things work because you were starting from the wrong premises. Back in the 1970s was the golden age of operating systems, when people were first figuring out access control architectures. And there was a fundamental split between the identity-based approach to access control architectures, represented by access control lists, in which every access decision starts with the question, who are you? Who is making the request to decide whether it's allowed? And there was the capability approach, in which the fundamental of it is that it approaches permissions as bearer rights, as rights that are fine-grained and individually transferable. Back in the early 80s, before we faced viruses and modern malware, before we understood what the security problem is that we need to solve, the industry ended up effectively choosing the identity-based fork in the road. And since then, we've been wandering in the desert for 40 years, trying to build secure systems, starting from that part of the search space. Well, one of the things that we know from the science of search algorithms is if you make a speculative choice before you know what you're doing, and then you search the subspace a lot and don't make progress, you have to consider the possibility that you're stuck in a cul-de-sac. And the identity-based approach to access control has some fundamental problems, some problems that seem unsolvable within those premises, that it only admits further tinkering that doesn't make overall progress. And we can understand the main one as excess authority. When a program runs on your computer, the program is running as you. When the program makes a request, the answer, should the request be allowed, is based on whether you are allowed to perform that action. So therefore, every program that you run that's allegedly running on your behalf is running with all of your authority. It can do everything that you can do. So the search algorithms say, well, if we're stuck in a cul-de-sac, what we should do is backtrack to the speculative choice that got us here and try out the other branch. However, having spent 40 years building up the entire software industry and with civilization now resting on that installed base, we can't simply throw out the entire 40 years of software that we've accumulated, go back to that choice point and rebuild it over again. So if we can't go forward and we can't go back, what should we do? Well, for non-security reasons, the fundamental formal properties of the capability path have been recapitulated by the rise of object-oriented programming and the rise of safe object-oriented programming languages. These things by themselves are not secure, but they provide a starting point for security, and they provide a starting point for the kind of security that would have descended had we made the other choice. But you can't simply start with a safe object-oriented programming language and start securing it and hope to make progress if, again, you have the wrong premises. And a case in point is Oak was the early Java. It was a memory-safe and statically type-safe object-oriented programming language with encapsulated objects. But to turn it into a secure programming language with the security that Java provides, they kept fiddling. They kept adding these epicycles. And the result, by the time they declared it secure, the security of Java was unusable, and Java is only used as a conventional programming language. It's not used to provide interesting security. What about JavaScript? Well, JavaScript starts even worse than Oak. In Oak, at least it was the case that a program could not change the definition of arrays. In JavaScript, any piece of code can engage in what's called prototype poisoning, can replace the push method on array prototype with some evil function that might exfiltrate secrets, for example. And then any other code running in that environment, when it tries to push onto an array, engages the attacker's code. So for those who think that JavaScript is just a hopelessly insecure place to start to create a secure programming language, I offer the following counterexample. Over here we have a function, makeCounter, written in JavaScript. I'll come back to the harden function later. Every time makeCounter is called, it creates a count variable and a record, and it returns a record of two functions, inker and decker, where the record operates effectively as an object where inker and decker are the methods of the object and count is the encapsulated instance variable. And every time makeCounter is called, it makes a new instance, and each of these instances is isolated from each of the other instances. The individual methods are separate permissions to manipulate the underlying counter. So for example, we can give an entry guard access to the inker method, an exit guard access to the decker method, and now the entry guard can only increment the counter, has no other ability. The exit guard can only decrement the counter. So the fundamental security mechanism here is these pointing relationships, are these memory-safe protected pointers to objects. And this is the fundamental logic universal to memory-safe object programming languages that recapitulates the original capability concepts. And even without further securing the language, in a memory-safe programming language, they already are they already provide a form of security. If object Bob does not start off with a protected pointer to object Carol, then Bob cannot make use of Carol's public API. If object Alice that does have a reference to Bob and a reference to Carol invokes Bob's foo method, passing Carol as an argument, what Alice is doing is she's both exercising the permission she has to invoke Bob's public API, and she's granting Bob permission to invoke Carol, after which Bob has the permission to invoke Carol's public API. So to get from this core logic of objects to object capabilities, all we have to do is remove the crap. All we have to do is remove all of the means by which objects can cause effects on the world outside of itself other than making use of these references, in which case these references are the only form of permission. They're the only means that an object can cause effects. And once we take that step, then the reference graph, familiar from the programming language literature, becomes identical to the access graph from the access control literature. And this becomes our first big step in reducing excess authority, which is simply that we design object interfaces naturally for modularity's sake, where we only provide as arguments the permissions, the other objects that the object, Bob in this case, needs to perform its work. We don't give it irrelevant access that it can abuse. The principle of least authority starts by taking this fundamental property and then building up patterns to actually design the API of Bob such that it's not given objects that enable it to do more than it needs to do to exercise its proper duties, to do its legitimate job. Due to a bizarre historical accident, JavaScript actually forms a better starting point than many other languages. Conway's law says any organization that designs a system will produce a design whose structure is a copy of the organization's communications structure. JavaScript started out as a language only for programming browsers, but it was split between two standards committees. ECMA was responsible for standardizing the language. W3C was responsible for standardizing the browser API. And this caused a split in functionality that's extremely analogous to the hardware division between user mode instructions and system mode instructions. The language was almost purely just computational, and then the browser API was provided by host objects like document and XML HTTP request and process that provides the ability to cause effects on the outside world. It provides the devices essentially for engaging in network I/O, for talking to the user, etc. And the result of this split is that JavaScript is host independent. It is now, it enabled other hosts to be defined, like Node, like JavaScript for embedded systems, like JavaScript running on blockchain, which is what Agoric is doing. JavaScript actually has several technical advantages over many other languages that help us secure it. But the main one, besides this user mode, system mode split, is that authority is reachable only by scope. The way JavaScript code gets access to these host objects, like document, is by looking up a variable in global scope, by looking up the name document in global scope. So if you can intervene in the global scope lookup, you're now in a position to isolate and confine code and then connect the code in ways that you can control. So I'm going to introduce hardened JavaScript in terms of three primitives. The first one is lockdown, which is the primitive that turns a normal JavaScript environment into a hardened JavaScript environment. And the main thing that it does is it hardens the primordial objects, the objects that exist before any code starts running, like array and array.prototype. After lockdown is called, you're now in a hardened JavaScript environment in which all of those primordial objects have been made immutable. Unsurprisingly, hardened JavaScript has a primitive called harden that we've seen before in our counterexample. And harden is about making API surfaces tamper-proof. It's a recursive application of Object.freeze by walking the public properties of the object and freezing everything found. So in this case, hardening the outer object here also hardens all of the nested objects. And then finally, compartment, which is the mechanism that we've introduced to intervene in global scope lookup so you can confine code into separate compartments. In hardened JavaScript, our previous prototype poisoning attack fails because array.prototype is immutable, and therefore the attacker cannot replace its push method. That only brings us back to the level of security that Oak provided, where the definition of the fundamental objects could not be changed by attacker code. Of course, hardened JavaScript retains the fundamental nature of JavaScript in which you can evaluate code, and code evaluates in some scope, and the free variables in the code are dereferenced according to that scope, including the variables in the global scope. When you create a compartment, you're creating an evaluation context with a new, fresh global object and global scope that contains nothing dangerous. And then code that's evaluated in that compartment is evaluated only within that global scope. So if it refers to variables that are not on that global object, that code fails. However, the creator of a compartment can endow the compartment with whatever global bindings it wants, and then code that evaluates in the compartment can refer to those global bindings to get the bindings according to the creator of the compartment. Why does this all matter? Well, let me start by explaining a way in which I've lied to you. JavaScript's user mode, system mode separation is not complete. The JavaScript language defines date that gives you the current time. It's a read-only channel, but it does violate this notion of system mode, user mode separation. It reveals the current time and thereby enables code to measure duration. So our compartment mechanism also fixes that. When you create a new compartment, the date of the global object of the new compartment is a safe date that refuses to give you the current time. But again, the creator of a compartment can endow the compartment with whatever powers it wants. So if the creator of the compartment has the powerful date, it can create a compartment endowed with the powerful date, which can then be used within the compartment. We demonstrate all this with the hardened JavaScript escape room challenge at this URL. And we invite everybody to accept this challenge, to try to break out, to try to escape from the escape room. So what do I mean by this? In this escape room, in that box, you can type whatever hardened JavaScript code you want, and it will run. It's running in a compartment controlled by the escape room itself, and what the escape room has provided to your code is a function that it can call where the duration of the function, the amount of time it takes that function to return, depends on the secret that the escape room knows and that your code starts off not knowing. And the challenge is to discover the secret by making use of that variable duration. You can run the escape room in two modes, one with the safe date and one with the powerful date. You've all heard about Meltdown Inspector, side channels which are subtle. The side channel here is egregious. It's really very, very noisy. If you can measure duration at all, it's easy to discover the secret. And so the challenge is to put it into the safe date mode, in which you're running in a compartment which has been denied all powers but has been given this function of variable duration, and see if your confined code can discover the secret. What this demonstrates is even within an address space, by denying special powers, including non-determinacy and the ability to measure duration, you can prevent code from reading side channels, even egregious ones. So how did we get to hardened JavaScript, starting with the JavaScript that we came across in 2007 when we started on this mission? That was the JavaScript known as ECMAScript 3, and it had some really, really horrible misfeatures that really made the overall task seem hopeless. In particular, it had non-static scoping. So what we did, we started with a thing very rare for a standards body. We started with a subtractive step. We introduced a strict mode that omitted the worst features of JavaScript. And strict mode is really only statically scoped. However, strict mode does not enable us to deal with things like the event stream incident, does not allow us does not help with those supply chain attacks, because it's still the case that all the primordials are mutable, so you can engage in that prototype poisoning attack. It's still the case that there's one global object on which all of the host objects are accessible. There are no compartments, and therefore we still have many of the problems of excess authority. So we use the enablers that we got into the JavaScript standard to create a further enforced subset of ES strict, which we call hardened JavaScript, in which all of the primordials are pure. They provide no ability to cause effects. And we introduce this compartment abstraction to intervene in the global scope lookup. And the result is it's close enough to JavaScript that the vast majority of JavaScript language is unchanged, and a tremendous amount of old code not written to run under hardened JavaScript, not written even aware of the existence of hardened JavaScript, nevertheless runs compatibly under hardened JavaScript. But of course, that old code, not knowing about hardened JavaScript, cannot make use of the special abilities of hardened JavaScript. So it's not doing anything special to help express interesting security properties. The point here is that new code that is aware of hardened JavaScript can be written making use of these abilities in order to control old code, starting with placing it into a compartment. But hardened JavaScript, having changed so little of JavaScript, still includes many confusing parts of JavaScript. These remaining confusing parts obey now the formal properties of capabilities. It still prevents one confined piece of code from attacking another, but it doesn't prevent the programmer, the author, from writing code where they're confused what the code means. The JavaScript is still a confusing language if you use the entire language. So we define an advisory subset of hardened JavaScript called Jessie that's really tremendously simpler and is a very pleasant language for writing programs in. And at Agoric, we write most of our code in the Jessie subset. So the hierarchy of subsets here is we started with the full standard JavaScript. We introduced into the standard ECMAScript strict. We introduced enablers that enable us to build hardened JavaScript out of JavaScript. And the compartments that we're providing, as we're about to see, are really featherweight. They cost almost nothing, just a few objects, so you can afford many of them. Inside that, we define this very small, clean sublanguage called Jessie. And it's small enough that it's easy to build a Jessie interpreter in any conventional imperative language. And Jessie is thereby simple enough that it can provide a standard for universal safe mobile code in the same sense that JSON already provides a standard for universal safe mobile data. So what does lockdown do? How does it transmute a JavaScript system into a hardened JavaScript system? Well, object capabilities, again, are all about the pointing relationships. These protected pointers are the permissions. And this is a representative sample of what the primordial heap looks like, what the pointing relationships are among the primordial objects. Let's get rid of the pointers that, now that I've shown it, let's get rid of the pointers that aren't that interesting. So in addition to this heap, there's the global object itself that contains the pointers into this initial primordial heap and associates them with global variable names. And the elements of that initial heap that are like the eval function and the function constructor are a special category. They were a category we call the evaluators. They have a special relationship to the global object in that they evaluate code. Code evaluates in a scope, and that scope is rooted in the global object. In addition, the global object is how hosts provide the system mode authority, the host objects like document. So document is dangerous as an ability to cause effects that is provided by the host. Date is part of standard JavaScript, so we still have to provide a binding for date, but the original date object itself is dangerous. Because these objects are dangerous and can be obtained from the global object, the global object is dangerous. Because the global object is dangerous and these evaluators evaluate code in the global object, the evaluators are dangerous. So what lockdown does is it quarantines these dangerous objects into the start compartment, into the initial into the initial context that code runs in, that still has a global object with these dangerous authorities. And it points into the frozen shared primordials, this primordial heap that's now locked down and frozen. And the key thing is that all of the pointing relationships between these two worlds are from left to right. The frozen primordials are completely self-contained. With access only to them, you can't get to anything else. And as a result, when you create a new compartment, that new compartment is much like the start compartment. It has a new global object that mostly just points into the shared primordials, except that it has to have its own evaluators that evaluate code in its own global object. And it has to have the virtual host objects, the powerful objects provided by the creator of the compartment that the code in the compartment might think of as global objects. So JavaScript for embedded is running hardened JavaScript. It's running in light bulbs, and the access to the bulb device itself is provided as a host object, and they're using hardened JavaScript to create multiple compartments in a light bulb and control access to the bulb device itself. The compartment abstraction itself, as we've seen, is an evaluator, and therefore we also have to introduce it, treat it like we treat the other evaluators. But altogether, this really does represent the overhead that is per compartment. It really is just a few objects, and mostly the code in the JavaScript environment is shared between all of these compartments. Returning to our MetaMask package dependency graph, we're working with MetaMask on Lava Mode, on a way to use hardened JavaScript such that each of the packages, each individual package is loaded into a separate compartment, and a static analysis of the package gives an initial analysis of what the endowments are that an individual package needs. We practice principle of least authority with regard to those initial endowments. So the green packages here are the ones that don't need substantial dangerous authority. Doesn't mean that they can't cause you harm, but you're taking much less risk on their flaws. The principle of least authority says, provide the least authority needed to do your proper job. For the job of some packages, that's still a lot of authority. So the packages colored red here are still the ones that have substantial authority, but now you can economize on your security review effort. You can more deeply examine the packages that are given more authority and therefore have a greater potential for abuse. And you can inspect them to see what authorities they are that they're dependent on, as well as what their connection is to other packages. So, in the progress of object-oriented programming for functionality's sake, we've come up with the industry has come up with a set of design patterns, and this has really improved our practice of object-oriented programming. This controlling code that uses hardened JavaScript to express security properties. We've also been accumulating an understanding of more and more security patterns over time, patterns that express and enforce security properties. So, for example, the read-only attenuator is one where Alice, let's say, is the controlling code, and she has a powerful file object. She wishes to give Bob read-only access to the file. So she creates an attenuator that re-exports only the query methods of the file, not the update method. and then she gives Bob access to the read-only file. An ultimate form of such intermediation is the membrane, where we create these attenuating intermediaries, the half circles here, using JavaScript proxies, and they grow on demand to maintain the connectivity separation between the blue objects and the red objects, so that they have no direct access to each other. And then we can starting from here, we can introduce many kinds of attenuation. A great example is revocation. Revocation is temporal attenuation. It's attenuation in time, where the boundary seems to not exist, is trying to be transparent until the revoking action. So we can abstract this to say that it's as if the boundary doesn't exist until somebody hits the plunge on the revoker object, hits the plunger on the revoker object, but once they do, all of the connectivity provided at that membrane boundary is severed, and the garbage collector is thereby able to collect everything within the boundary because nothing can any longer point at it. So far, I've shown only small examples, as any talk like this must, but at Agoric we're doing serious systems building using hardened JavaScript. Over here, we see where hardened JavaScript is in our layering of abstractions, our layering of endpoint abstractions and the layering of protocols that go between them. Hardened JavaScript, together with the CapTP protocol, Capability Transport Protocol, running on IBC, form a distributed object protocol, and hardened JavaScript, together with CapTP, form Endo, distributed secure hardened JavaScript, using this cryptographic distributed object protocol. And then on top of that, we build digital assets, a smart contracting framework, and then those scary DeFi financial abstractions are then running on top of our smart contract framework. And to give you an idea of how good a basis object capability programming is for creating the rest of that system that we're building, this is the core logic of the money that we're creating, of the one kind of the digital assets that we're building on top of hardened JavaScript. The actual one that we're running is substantially more complicated than the code shown here, but the code shown here is real code. It really works. It really does have the security properties desired of a cryptocurrency. And it's built using only the elements I've already explained. And on top of that, we're not only building the financial abstractions for our users to use, we're also building the financial abstractions, lending protocols, staking systems, various kinds of incentive reward systems that our chain itself rests on. The incentive structure creating the replication between our validators, giving us a credible chain, is itself an incentive structure built on our own DeFi abstractions. And as we've been going, we've been subjecting all of this to security reviews, and we've been publishing those as we go. And we do find flaws. Those security reviews do find flaws. We fix them as we go. But so far, the security reviews have very much been confirming for us that we got the premises right, that the object capability foundations and the philosophy that they bring is a good starting point for building such systems. And in fact, the object capability philosophy generalized is also how we approach security at the financial level, which is itself the subject of what could be a whole other talk. But instead, I'll now break for questions.
Great, thank you, Mark. So we had a few questions, and I think I'll start with the one I thought was the most interesting one, which was for a supply chain attack, would the endowment discovery phase be susceptible to being duped by excess authority?
Yes. That's what the red dots are about. But there's a further aspect of the whole lava moat system that I didn't talk about, but that's crucial to answering your question, which is the differential analysis. There's this acronym in computer security called TOFU, trust on first use. Trust is, of course, too strong. We should, but there's the system that you looked at, where you took a look at what those excess authorities are, and for whatever reasons, you decided maybe after fixing some things, maybe after replacing some things, maybe after some interventions, you've decided to risk it and go with that supply chain, with the initial authorities provided by that analysis. Having done that, you capture those decisions so that when there are upgrades, like some linear algebra package or a parser generator that now wants network access or access to your file system, the upgrading to that flags the demand for authority according to the current analysis that's beyond the authority that the previous analysis provided, and the previous analysis is what you reviewed. And then when you see that, oh, why does this linear algebra package need network access or need to access my file system? Hopefully that's a red flag. Now, admittedly, to most customers, it won't be a red flag. So we still depend on the social processes of software development, but we want to make it more obviously a red flag to more developers so that the danger gets caught earlier, so that the remaining developers can be made aware of those dangers.
Great, thank you. So another question had to do with essentially contrasting this, I guess, to the traditional approach, or perhaps melding it with the traditional approach. How should we think about the efficacy of the hardening approach versus signing scripts or binaries to prevent non-approved versions from executing at all? I mean, is there any role for combining those, for example?
Yes, in fact, it's necessary to combine those. We don't want to depend on NPM telling us that the code we're installing is the same as the code that we approved. We want to, there's something called sub something integrity. I'm sorry, I'm not remembering the term. But basically, we want to accumulate hashes, transitive hashes, across dependency graphs and ensure that the code that we believe that we believe corresponds to code that we examined is code that has the same hash. So we are in fact assuming those protections as well. It's a necessary, all that code hashing and remembering those hashes is a necessary part, but not sufficient by itself.
Right, and was the term you were thinking of sub-resource integrity?
Yes, thank you.
Thanks to Jordan who pointed that out. Another more basic question, which which is was on the technical side, was your example of essentially encapsulating things so you couldn't get it, couldn't figure out the duration and so forth. And the literal question was, wouldn't you be able to tell time by sending message back to the client on an interval? And you should be able to explain that away.
Yes, thank you. Great question. Set interval and set timeout are not part of the standard JavaScript language. They are defined as part of the host. Now, they're provided across many hosts, and therefore there will be much code will depend on the existence of something like that. But now it's like the controlling code providing a virtual bulb, providing virtual host objects that operate according to the controlling code's decisions. So you can provide or deny or virtualize set timeout and set interval as you wish. A bigger issue is sources of non-determinacy. So we actually introduced a proposal to JavaScript that is now part of modern JavaScript that provides another source of non-determinacy as part of the language, and thereby provides a really quite a bad side channel, which is weak references and finalization. Enable code to sense garbage collection. It's not a duration side channel, but it is a non-determinism that can be used to leak secrets. And we treat, the hardened JavaScript treats weak references very much the way it treats date, that only the starting environment has the powerful weak reference constructor and finalization registry constructor, and compartments by default do not. Now, the other thing that's important in answering that question is that many applications, I would say most applications, any application that needs access to the network or access to the user has inherent sources of duration measurement. It doesn't have to be a clock. It can be network round trips or interaction through the DOM. Those also enable the measurement of duration that subverts the confinement shown here. So the important point is not that we can deny applications the ability to read duration, but we can deny it to a substantial number of packages. Many packages, linear algebra libraries, parser generators, on and on and on. There's a tremendous number of packages that are just transformational, that don't need anything non-deterministic in order to do their proper job. Some of them will, and those can still read side channels.
Thanks. I guess we have time for probably one more. So the question is, why did Agoric choose JavaScript as opposed to, say, Solidity, and what are the benefits that you think that you get from that?
So Solidity is also, the premise is, again, identity-based access control. The primitive in Solidity, where the identity check is hiding, is something called message.sender. In Solidity, anyone can send a message into any contract. Therefore, the contract can get a message from anywhere. And therefore, the contract, in order to know what to do with the message, must have some other means for deciding how to regard the message. In an object capability system, an object can only get a message from someone with a reference to the object, and therefore the reference to the object is adequate demonstration that you've been given legitimate permission to invoke the object. In Solidity, it's this message.sender, which reveals the identity of the sender, the immediate sender. So it's sort of the top of the stack, the immediate caller on the stack. There's another one called transaction.owner or transaction.origin, which is the bottom of the stack, the external user that it came from, message.sender has tremendous failures to compose. It's a tremendous cost on expressivity. Transaction.origin has tremendous failures of excess authority. And we've seen both in the failure modes of Solidity contracts. In fact, one of the reasons why I left Google to form Agoric was watching these exploits of Solidity contracts and thinking, if only they were doing it our way, many of these attacks would not even have been possible. Some of them obviously would have been. The object capabilities don't magically solve the problems, but many of the attacks simply would not have been possible. And everything we've seen since then has reinforced that notion.
All right, we're perfectly on time. We just have, though we do have more questions, but we'll have to leave them for another time. And this is the perfect opportunity to thank Mark for spending the time with us for a very illuminating and interesting talk. And I hope everyone enjoyed it. And thank you. And maybe we'll be able to twist your arm and come to talk to us again sometime.
I would enjoy that.
Very good. Thank you, everyone.